MHF4U, Grade 12 Functions, Section 3.3. Today we'll be discussing the characteristics of polynomial functions in factored form. So first of all, let's start with some definitions. When we talk about the order of a function, it's the exponent to which each factor in an algebraic expression is raised. So for example, an f of x is equal to x minus 3 squared times x minus 1. The order of the first term is 2 because that's the degree that, or that's the exponent to which that term is raised to. And then for x minus 1, the order is 1 because that's the order to which the term is raised to. A family of polynomial functions is a set of polynomial functions whose equations are the same degree and whose graphs have common characteristics. So for example, one type of quadratic family has the same zeros or x-intercepts. Okay, so then we get to a summary of the main ideas for this section. So the zeros of the polynomial function y is equal to f of x are the same as the roots of the related polynomial equation f of x is equal to 0. And we see this idea here with this quadratic function and the related linear function, for example. Okay, so we need to know a couple of things. To determine the equation of a polynomial function in factored form, follow these steps. So you want to substitute in the zeros into the general equation of the appropriate family of polynomial functions in that form. Then you want to put in the coordinates of an additional point for x and y, and then you want to solve for a. So remember, it's actually really simple. All we're doing is, first of all, we're finding the points for the zeros, which include these points right here. And then we want to find the value for a, which would represent this point right here. So in order to solve for this point, we need to just find another additional point. And we're going to put the x and y values in for those points. And once we do that, we can then solve for a, and we can find the equation of our quadratic. Or, quadratic or cubic or whichever polynomial we're dealing with. And then if any of the factors of the polynomial function are linear, then the corresponding x-intercept is a point where the curve passes through the x-axis. So the graph has a linear shape near this x-intercept. So this is really interesting. Basically, based upon the behavior of each piece, each factor that comprises your overall polynomial function, you can actually tell what the behavior will be at the zero. So for example, in this case, we have a linear term, right? So that means that when the curve is, crossing the axis, the x-axis here, it's crossing it in a linear form, right? So if we see here on the zoomed in graph, this looks almost linear, right? And similarly, depending on the order of the term, let's say we're second order or third order, it would enter the function accordingly, which is what we see in the next point right here. So if any of the factors of a polynomial function are squared, then the corresponding x-intercepts are turning points of the curve, and the x-axis is tangent to the curve at these points, which is what we see right here. So in this case, this corresponds to our term with x plus 3 squared, which would mean that the 0 is at -3, and we can see the behavior at this point is similar to that of a quadratic because it's second order. And lastly, if any of the factors of a polynomial function are cubed, then the corresponding x-intercepts are points where the x-axis is tangent to the curve and also passes through the x-axis. The graph has a cubic shape near these x-intercepts. So again, if we look at this piece right here, it has a cubic shape. In particular, this area right here has a cubic shape, and this corresponds to the first term right here, x plus 3 cubed. Okay, so now we have some examples. So the first one is, match each equation with the most suitable graph and explain your reasoning. So I have some questions on the right that you need to ask yourself every single time you get a question like this. The first thing is, what is the degree of the function? Next, what is the leading coefficient? And lastly, what are the zeros? So in this case, for part A, we'll go by function. So for function A, right here, we can see that this function is of second degree, and that there are two terms that are in this, right? We have the first term being of second order, and the second term being of first order, which means that we're looking for something that has both a quadratic behavior and then a linear behavior. Furthermore, we know that the zeros are at -1 and at 3. So let's look for something with zeros at -1 and 3. In this case, the answer is C, and we can see that we have a 0 at -1 and at +3. And the next thing we can see is the behavior. So you might be comparing, between this and the other examples that are here. Well, why is the answer C? Well, you can see the behavior at -1 is that of a quadratic, right, which matches our second order right here. And then for the behavior at 3, it's linear. And lastly, we can look at the leading coefficient, and we can see that because it's leading coefficient of 2, it's positive, and there's a vertical stretch by a factor of 2, which means this cubic function will be upward facing, and would be moving from the first quadrant onwards. So these are all hints that we can have that help us, figure out which graph corresponds to the function. So following the same logic then, we can see that the part B corresponds to graph A, and then the equation for part C corresponds to graph D, and the equation for part D corresponds to graph D. Okay, so then we want to sketch a possible graph of each function. So here I've already sketched them out, but there's a couple of things that you have to consider when you're sketching the graph. The first one being the zeros. So the first thing you want to do is figure out what the zeros are for the function. So here we know it'd be 4, it'd be 1, it'd be minus 5, which is what we have right here. This is the 4, this is the 1, this is the minus 5. And once you have the zeros figured out, the next thing you want to look at is the overall degree of the function. So here I know it's degree 3. How do I know that? Because I multiply through the x value. So I have 3 x's here. And once I multiply those through, I know I have something that looks like x cubed. So in order to expand this whole thing out, I would get x squared, I would get x cubed times I'd get x cubed plus x squared, etc., etc. So you would have the terms with with those degrees associated with it. And the last thing we're going to look at is the vertical aspect. So here we see there's a vertical reflection happening, and that's how we know it's moving from the second quadrant out to the fourth quadrant. So once you put those points together, you can sketch your approximate graph. Now, you might be wondering, well, how do I know where the maxima and minima are? And that comes on later. So for this step right now, you don't really need to worry about knowing how to calculate maxima and minima, but you will learn that eventually in your calculus class. And then for our second function here, we use the same ideas. So again, we know our zeros are at 0 and at positive 6, which is right here. And then we want to look again at the overall degree of the function and at the order of each term. And that helps us figure out what our graph would look like. And these are really zoomed out, but if you were to zoom in on each point, you can see what the behavior would be as the function enters and exits those points. Okay, so then we're going to write the equation of each function. So I did example A here. And so for example A, the first thing you want to look at is that the leading coefficient is positive. Next thing you know is that it's the third degree function. It's cubic based on the shape we see is very similar to our cubic function. The next thing we can see right away is that our zeros are at -3, at 2, and at 5. And so this gives us information as to how we can calculate our overall function. So as I mentioned previously in our summary as to how we can calculate the function given our points, given a graph, we now want to put in our zeros. So we put in our zeros right here. And this is in factored form. And now the only thing we need to solve for is our a. So we can use any point given to us. In this case, in the example, they gave us 0.18, so perfect. So we set our y equal to 8 and our x equal to 1. And once we do that, then we can solve for a. So it's quite simple. We solve these, we isolate everything out. We get 16 times a is equal to 8, so a is equal to a half, and that gives us our overall function. F of x is equal to half times x plus 3 times x minus 2 times x minus 5. And so that's it for this section. We've gone over how to find graphs of functions, how to find equations of functions given the graph, and we've also looked at how the behavior at each term comprising a polynomial function can affect its overall graph. So thanks for watching, and if you have any questions, feel free to contact us on passionateminds.com. Thank you.